Hello and welcome to this revision session for AQA A-Level Physics on the topic of electricity, which is found in paper 1 on current, resistance and resistivity. So if we've been successful and we've learned in this revision session, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? When complete your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the questions in the revision session. When you're doing this, make sure you write your answers in full sentences and show the full working out. Now in the right hand side section, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So for some tips for your revision, how can you be independently revising A-Level Physics? Well, the first step is to learn the key facts. Use revision guides, class workbooks, prep notes in the textbook to learn the key ideas of the course. You may wish to make mind maps or write out the notes yourself. Secondly, test yourself. So use things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge. You may wish to do this from your own cue cards. Then finally, step 3 is to practice. Use exam prep books, homework books, study books, additional workbooks to answer exam questions and mark your own work. So you may wish to download your own exam past papers to do this. So you should be doing the 3 steps of learn the key facts, testing yourself and practicing exam style questions. Now in this revision session we're going to be looking at 2 types of questions, key check questions and then examination style questions. So let's have a look at these key check questions. So to assess your understanding for all of these questions, they're short, sharp questions which will test your key knowledge. So look at the following. What is the current in this circuit and how is the current produced? So pause the video now, then unpause the video when you want to go through your answer. Now current is the flow of electrons around the circuit due to a voltage acting across the circuit. Now what is producing the electromotive force in the circuit to cause a current? Pause the video now, then unpause the video when you want to go through your answer. Well, the battery or the power source and the outer charge of the wire produces an electromotive force to produce a current. The next question. Why does the power source not produce an electromotive force when it is not switched on? So pause the video now, then unpause the video when you want to go through your answer. Right, the power source produces an electrical field when it's turned on. So when switched off, the overall electrical field produced by the power source is 0, so you're not going to get an electromotive force. The next question says, what is the size of the current in this circuit? And what does this tell you about the free electrons? So pause the video now, then unpause the video when you want to go through your answer. Well, in a series circuit, the current is constant. So this means that the free electrons are moving through the circuit at a constant rate. The next question says, why is the current constant in a series circuit? So pause the video now, then unpause the video when you want to go through your answer. Right, the current is constant as the electromotive force in the circuit is constant as the power source and wires are producing a constant electrical field when switched on. The next question says, why do bulbs turn on immediately when the circuit is complete? So pause the video now, then unpause the video when you want to go through your answer. Right, there are free electrons everywhere in the circuit and there are electrons immediately where the bulbs are. So we'll move through it almost instantly. The next question says, why do the bulbs light up when electrons move through them? So pause the video now and unpause the video when you want to go through your answer. So the free electrons will collide with the metal ions in the bulb. This dissipates the electrical energy as thermal energy and this heats up the filament, causing it to glow. The next question says, if the power source is provided the circuit with 12 volts, what should the overall potential difference of the bulbs combined be and why? So pause the video now, unpause the video when you want to go through your answer. Right, the combined potential difference should be 12 volts as electrical energy is conserved in the circuit. The next question says, in reality, why will the combined potential difference of the two bulbs be less than 12 volts? So pause the video now, unpause the video when you want to go through your answer. Right, as the electrons travel through the circuit and the power source, they will collide with their ions, causing the energy to be dissipated from the circuit before it reaches the bulbs. The next question says, could an electrical current of protons be produced, and why? So pause the video now, then unpause the video when you want to go through your answer. Right, yes it could, because protons are charged and the electrical field of the power source and wire will interact with any charged particles placed inside of it. The next question says, what is resistance in the circuit and how is resistance produced? So pause the video now, then unpause the video when you want to go through your answer. Right, resistance is the impedance to the flow of charge in an electrical circuit. It's produced by the collisions between electrons and ions in the material that they are moving through. The next question says, what is the link between resistance and the length of the material and why? So pause the video now, then unpause the video when you want to go through your answer. Right, the resistance and the length of the material are directly proportional. As the longer the material the electrons travel through, the greater the number of collisions between the electrons and the ions. The next question says, what is the link between resistance and the cross-sectional area of the material and why? So pause the video now, then unpause the video when you want to go through your answer. Right, the resistance and the cross-sectional area of the material are inversely proportional. As the greater the cross-sectional area of the material, the lower the density of collisions between the electrons and the ions, lowering the resistance. The next question says, what is the link between resistance and the temperature of the material of a conductor and why? So pause the video now, then unpause the video when you want to go through your answer. Well, the resistance and the temperature of the material of the conductor are proportional. The greater the temperature, the greater the amplitude of vibration for the ions, the greater the number of collisions, so the greater the resistance. The next question says, what happens to the resistance of a bulb as it is being used and why? So pause the video now, then unpause the video when you want to go through your answer. Well, the resistance of the bulb increases as the temperature of the bulb increases as it is being used. The next question says, why does a filament bulb not follow Ohm's law? So pause the video now and unpause the video when you want to go through your answer. Well, the filament bulb does not follow Ohm's law as the resistance does not stay constant over its operating voltage because it is heating up. Now the next question. What is the link between the resistance of a material and its output potential difference, and why is this? So pause the video now, then unpause the video when you want to go through your answer. Right, the resistance and the output potential difference are directly proportional. As the greater the resistance, the greater the energy dissipated through the device, the greater the potential difference of the device. The next question says, what is a superconductor and how is this achieved? So pause the video now, unpause the video when you want to go through your answer. A superconductor is a device with no resistance as there are no collisions between the electrons and the ions of the conductor. So why is there no resistance when a current is not flowing in a circuit? So pause the video now, then unpause the video when you want to go through your answer. Now, when there is no current, the electrons still move in random directions and collide with ions. However, there's no direction they should be moving in, so no impedance to the movement in a direction. The next question says, looking at the two wires, which would generate the larger resistance for the same potential difference and why? So pause the video now, then unpause the video when you want to go through your answer. Well, the larger the wire, the more you would generate a resistance for the same potential difference, because there are more ion charge carrier collisions as the wire itself has more ions. Now, both of these wires are made from copper. Would they have the same resistivity for the same potential difference, and why? So pause the video now, then unpause the video when you want to go through your answer. Right, they would have the same resistivity as they are the same material, and the resistivity is independent of the length and the cross-sectional areas of the objects. Now, both wires are heated. What would happen to their resistivities and why? So pause the video now, then unpause the video when you want to go through your answer. Now both resistivities would increase, as increasing the temperature increases the amplitude of ion vibration in the wire, so there'd be a greater frequency of charge carrier ion collisions. Now when A is double the length of B, what would the difference in their resistances be and why? So pause the video now, then unpause the video when you want to go through your answer. Well, wire A would have double the resistance of wire B, as resistance and length of a wire are directly proportional. Now wire A is double the length of wire B. What would the difference in their resistivities be and why? So pause the video now, unpause the video when you want to go through your answers. Well, the two wires would have the same resistivities as they are made of the same material. Now, how can wires have different lengths but the same resistivity? So pause the video now, then unpause the video when you want to go through your answer. Now, as the length of the wire changes, the resistance of the wire also changes to ensure that the resistivity of the material stays constant at all times. So, what is the relationship here between the cross-sectional area and the resistance of a wire, and why? So pause the video now, then unpause the video when you want to go through your answer. Now, as the cross-sectional area of a wire increases, the resistance decreases. They are inversely proportional, as the charge carriers are more spread out in the wire, so there is a smaller frequency of collisions with the ions of the wire. Now, what is the relationship between cross-sectional area and the resistivity of a wire, and why? So pause the video now, then unpause the video when you want to go through your answer. Now, the resistivity and the cross-sectional area of a wire are not dependent on each other, as the resistivity of a material is constant for the same temperature. So now we've looked at the general check questions on this concept, let's have a look at some exam-style questions. So to start us off, describe the difference between resistance and resistivity. Calculate the resistance of a copper wire of length 1.0 meters and a cross-sectional area of 3.32 times 10 to the minus 6 meters squared, where the resistivity of copper is 1.7 times 10 to the minus 8 ohm meters. Explain the effect of changing the temperature on the resistivity of a metal, and calculate the resistivity of a piece of wire when it has a resistance of 170 ohms, when it has a length of 12 meters and a radius of 3 millimeters. So pause the video now, then unpause the video when you want to go through your answer. Right, so the difference is that resistance applies to a particular component, whilst resistivity is a property of the material itself. In the next question, resistance is equal to resistivity times by length over area. Now you're given all the values in the question, so you pop them into the equation, and it's 5.1 times 10 to the minus 3 ohms. Now when the temperature of a metal is increased, it's a conductor, the positive ions in the metal have more energy. So the positive ions will vibrate with a greater amplitude. You'll get a greater frequency of charge carrier and ion collisions, so therefore the resistivity has increased. Now this next question is going to be a bit harder. Now firstly, you need the area. So the cross-sectional area is pi r squared. Now we've got to change our radius of 3 millimeters into 3 times 10 to the minus 3 meters. We assume it's a circular cross-section, so therefore it's pi r squared, so it's 2.82 times 10 to the minus 5 meters squared. Now resistivity is resistance times by area over length. Pop in all the values, work it through, and it's 4.0 times 10 to the minus 4 ohm meters. The next question says, the critical temperature of tin is minus 269 degrees Celsius. The resistivity of tin increases as the temperature rises from minus 269 degrees Celsius. Define the resistivity. State the significance of the critical temperature of a material, and a sample of tin in the form of a cylinder of diameter 1 millimeter and length 4.8 meters has a resistance of 0.70 ohms. Use this data to calculate a value for the resistivity of tin. State an appropriate unit for your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so the definition of resistivity, it can be done in two ways. You could state that resistivity is the property that describes the extent to which a material opposes the flow of an electrical current going through it. Or you could say it is the value of resistance generated for a length of 1 meter and a cross-sectional area of 1 meter squared. Don't forget to use the word cross-sectional area. Now the critical temperature is one where below the critical temperature you will get no resistivity or resistance, and the device becomes a superconductor. Now in the next question, we know that resistivity is equal to the resistance times by the area over the length. Now again, to work out our area, we assume, because the cross-sectional area is pi r squared, it's a circle, the diameter needs to be halved to get to the radius, and we need to convert our millimetres into metres. So when you work it through, you get 1.15 times 10 to the minus 7 ohm metres. The next question says, sketch a graph of I against V for a metallic conductor at a constant temperature and use it to describe Ohm's law. The current in a resistor is 0.50 amps and the potential difference across it is 5.2 volts. Calculate its resistance. Define the ohm and express it in base units. Then a length of wire is connected to a cell. The current in the wire is 80 milliamps and the PD across the wire is 2.4 volts. Calculate the resistance of the wire. Then a resistor has a resistance of 1.2 kilo ohms. In 3 minutes, a charge of 54 coulombs flows through the resistor. Calculate the potential difference across the resistor. Then finally, the current in a filament lamp is 1.5 amps. It is operated for a time of 1 minute. The charges flowing through the lamp transfer 500 joules of energy to the lamp. Calculate the resistance of the lamp. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we should know that for a metallic conductor, I against V is a straight line through the origin, because V is directly proportional to I for a conductor at constant temperature. That is Ohm's law. Resistance is V over I, you should be aware of that. So pop the values in, you get 10 ohms. Now you can define the ohm in terms of the equation, R equals V over I. So 1 ohm is the resistance of a component where a potential difference of 1 volt is produced per 1 amp of current. Now you can work through your base units, so 1 ohm is 1 kilogram metre squared, seconds to the minus 3, amps to the minus 2. In our next question, once again, R equals V over I. Now remember, milliamps have to turn into amps, so it's 80 times 10 to the minus 3. So we get our answer to be 30 ohms. In our next question, we've got to use multiple equations. So we know that I equals Q over T. Now again, time should be in seconds, not minutes. So 3 minutes becomes 180 seconds. 54 over 180 is 0.30 amps. V equals IR, 0.3 times by 1200 kilo ohms into ohms. So you work it through to be 360 volts. And it's the same for the next question. We know that V is equal to the work done over the charge. Now charge is equal to IT. So therefore it's 500 over 1.5 times by 60. Because we don't work in minutes, we work in seconds. So we get 5.55 volts. R equals V over I. We've got V, we've got I from the question. So you work it through to be 3.7 ohms. Now our next question is an examination style question. So in a research facility, engineers are working with an experimental superconducting transmission cable. The cable is cooled using liquid helium to below its critical temperature, allowing current to flow with zero resistivity. The cooling system uses negative temperature coefficient thermistors as sensors embedded along the cable to monitor temperature changes. These sensors are connected to a control system that adjusts the flow of the coolant. Occasionally, the engineers notice sudden non-linear fluctuations in the resistance readings of the thermistors and an unexpected increase in the energy loss in the cable. So discuss the physical principles that could explain why the thermistor resistance varies with temperature and how this property makes it useful in this context. Suggest what might cause the non-linear fluctuations in resistance observed during operation and explain how they could be related to the behavior of the superconducting cable. Then discuss the advantages and practical challenges of using superconducting materials in power transmission systems like the one described. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, we know that NTC thermistors have a resistance that decreases as temperature increases. Now this is due to the increased availability of charge carriers or electrons into the circuit as the temperature rises. So this allows for an accurate monitoring of small temperature changes near the critical temperature, which is what is needed for this context. So in the cryogenic system, this enables the automatic control of the coolant to maintain the superconducting conditions required. Now for the next question, the fluctuations can indicate to you that the cable temperature must be approaching or even exceeding the critical temperature. Now exceeding the critical temperature is important as it will cause the material to lose its superconductivity and again it will regain resistivity, resulting in some energy loss. Then the thermistor's non-linear response could be due to the fact that there's a change in thermal environment, that the temperature changes rapidly, or that there's a feedback system delay when you're using the thermistor. Now in the last part of the question, superconductors, you've got to be aware, eliminate resistive losses, allowing for extremely efficient power transmission. They can also generate strong magnetic fields without energy losses, but the challenges include maintaining very low temperatures, it's very expensive, and it's unstable near the critical temperature itself. So the next question says, a surveillance drone is designed to operate at very high altitudes, where ambient temperatures fall below minus 60 degrees Celsius. The onboard electronics are protected by an automatic heater system triggered by an embedded NTC thermistor. On the ground, where the temperatures are much warmer, the thermistor has a resistance of 1,800 ohms. At altitude, when the drone stabilizes in very cold conditions, the resistance of the thermistor increases to 4,000 ohms. The thermistor is wired in a circuit with 1,200 ohm resistor and a 12-volt battery supply. When the voltage across the thermistor rises above a certain threshold, the heater activates. So explain how the use of an NTC thermistor in this system ensures that the heating is activated only under low temperature conditions. Given that the change in resistance is from 1,800 ohms to 4,000 ohms, discuss what happens to the voltage across the thermistor and whether this will cause the heater to activate. And then suggest one limitation of using this type of resistance-based switching system in an environment with rapid temperature changes or electrical noise. So pause the video now. Then unpause the video when you want to go through your answer. Right, in this first one, once again, we're looking at how a thermistor works. So as a thermistor's resistance increases as the temperature decreases. So this means, in this context, as the temperature drops, the increased resistance affects the voltage across the thermistor. Now this voltage can be used as a signal to activate the heater, ensuring it only turns on when it's cold. Now in the next question, on the ground, the lower the resistance of the thermistor means the voltage across it will be lower, because we know V is proportional to R. Now at high altitudes, the thermistor's higher resistance causes the voltage across it to increase. So the increased voltage indicates that the system must be cooler, because we know the link with resistance. So if the voltage rises past a predetermined trigger level, the heater will then be activated. So therefore the change in resistance going from 1,800 ohms to 4,000 ohms suggests that the voltage has increased significantly because the temperature has dropped significantly, triggering the heater to work in colder conditions. So you've got to link how a thermistor works to the actual context of the situation. Now in our last part, the system could be sensitive to small fluctuations in resistance due to electrical noise interference or instability in rapidly changing conditions. So this could cause the unintended activation or a failure to trigger the heater at the correct temperature, which would mean it wouldn't work as appropriate. The next question says, a new carbon composite material is being tested for use in remote infrastructure monitoring systems. The material forms part of a sensor cable embedded in concrete. Engineers expect the resistance of the sensor cable to change with both temperature and strain, allowing them to monitor structural integrity and environmental conditions. Now, a section of the cable has a uniform length of 1.50 meters and a diameter of 2.00 millimeters. At a baseline temperature of 20 degrees Celsius, the resistance is measured to be 12.8 ohms. On a hot day, the resistance rises to 15.2 ohms when the ambient temperature is 45 degrees Celsius. The material has a temperature coefficient of resistance alpha, which is equal to 3.2 times 10 to the minus 3 Celsius to the minus 1, where we know that the resistance at a certain temperature is equal to the baseline resistance times by 1 plus the coefficient temperature times by the change in temperature. Now again, this equation isn't given to you or expected to be learnt, in your exam, but you can use it because they've given it to you in this question. So, calculate the resistivity of the material at 20 degrees Celsius, determine the resistance expected at 45 degrees due to the temperature alone, and compare your result with the observed resistance and comment on what this suggests about the sensor cable, and then suggest one reason why the resistivity of this composite may not behave identically to that of a pure metal over wider temperature ranges. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we need to work out resistivity. First thing we need to do, work out the area. We assume the cross-sectional area is a circle, so it's pi r squared. So we get our diameter, we half it, we turn it into meters, so we get 3.14 times 10 to the minus 6 meters squared. We know that resistivity is resistance times by area over length. We have all the values now, so it's 2.68 times 10 to the minus 5 ohm meters. Now in this next one, we've got to use the equation given to us in the question. We know that the change in temperature is 45 minus 20. It's going from 20 to 45, so the change is 25. So therefore, the resistance at 45 degrees is 12.8 times by 1 plus 3.2 times 10 to the minus 3 times by 25. So it's 12.8 times by 1.08, which is 13.82. Now the observed resistance in the question is given to be 15.2 ohms. So the resistance observed is greater than the temperature alone. So therefore it suggests that the sensor cable must have experienced strain, it's stretched out, there's been a dimensional change, it's increased its length, so the resistance has gone up. Now the last question, composites often include insulating phases or irregular structures that can affect charge flow. So this can lead to non-linear or unpredictable resistivity changes with temperature, unlike the predictable behavior of pure objects. The next question says, an engineer is designing a compact power supply unit for an experimental sensor array. The design requires a current limiting component that adjusts the flow of current depending on the operating conditions, including changes in ambient and internal temperatures. To assist with the component selection, the engineer examines the current voltage characteristics for 3 components under test conditions: a metal wire kept in a thermally regulated housing, a filament lamp, and a semiconductor diode. A summary of the behavior is observed. Component X, the current increases proportionally with voltage over the measured range. Component Y, the current initially rises but begins to level off as the voltage increases. Component Z, little current flows until a certain voltage is reached, after which the current increases rapidly. So identify each component and explain the physical reason for the behavior observed in each case. Discuss the limitations of applying Ohm's law to each of the 3 components in this context. Then the engineer selects component Y for current limiting protection against overheating. Evaluate this choice, and in your answer consider how the electrical behavior of the component responds to change in physical conditions and whether it's suitable for this role. So pause the video now, then unpause the video and you want to go through your answer. Right, in this first one, what do we know? Well, component X is the metal wire. There's a linear IV relationship indicating a constant resistance, or it follows Ohm's law. This is because the metal is temperature controlled, so it keeps the resistivity constant. Component Y is the filament lamp, because the current increases more slowly at higher voltages because there's an increasing resistance. This is due to the heating of the filament, which increases the resistivity. Whilst component Z is the semiconductor diode. There's a very low current until the threshold is passed, then the current increases sharply. So it's caused by its structure, which permits conduction only after the forward bias voltage is reached. Now, the next one, you can understand that Ohm's law only applies to constant physical conditions and the fact that I is proportional to V. Now, only the metal wire will satisfy this since the temperature is kept constant. Now, the lamp and the diode are non-ohmic because their resistance will change with temperature or voltage. So in their cases, Ohm's law does not apply. Now, finally, the filament lamp, which is component Y, increases in resistance with temperature, so it naturally will limit the current as it heats up because the resistance is increasing. So this can protect the circuit by reducing the current flow under the high temperature conditions. Whilst it's not particularly precise or accurate, it is practical and it's a good passive method for protection, so it's suitable where you don't need a complex control system. The next question says, a design engineer is testing a battery-powered heating element using a medical emergency kit. The element is activated for 45 seconds to warm a gel pack. A microcontroller records the following measurements during the activation period. A steady current of 2.4 amps flows through the element. The potential difference across the element is 6 volts. The total energy transferred to the gel pack is recorded as 650 joules. After reviewing the data, the engineer suspects that either the current or the energy reading may be inaccurate and decides to investigate further. Firstly, define electrical current and potential difference in terms of fundamental quantities. Using the data provided, determine whether the energy reading is consistent with the values of current, potential difference and time, and show your reasoning. Determine the resistance of the heating element during operation, and then the engineer suggests that the energy reading may be too low due to the internal resistance within the battery. Evaluate this suggestion using relevant physical principles to support your conclusion. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to know how to define key terms. So electrical current is defined as the rate of flow of charge. I is equal to change in Q over change in T. And potential difference is the work done per unit charge. or V is equal to W over Q. Now we know from the information provided that the power is equal to voltage times by current, so it's 6 times by 2.4 from the information given to you, so that's 14.4 watts. Now energy transferred is power times by time, so it's going to be 14.4, what we just calculated, times by 45 seconds, so it's 648 joules. Now given that the value stated in the question 650 joules, that's very close to the calculated value, indicating that yes, the energy reading is consistent with the current and the potential difference. In our next question, we know R equals V over I, so it's 6 over 2.4, so it's 2.5 ohms. And then finally, if the battery had an internal resistance, well then the terminal voltage will be lower than the EMF when the current flows. So this means the external circuit would receive less energy than expected from the EMF alone. However, in this case, the measured energy actually matches the calculated value from the terminal voltage times by the current times by the time. Therefore, in this case in particular, the suggestion is unlikely because the internal resistance would cause a discrepancy in the energy reading, which is not really observed here. The next question says, an engineering team is testing a prototype wearable heating vest designed for mountaineers. The vest uses resistive heating mesh powered by a rechargeable lithium battery. During testing, the team records the following data. A steady current of 1.5 amps flows through the heating mesh. The potential difference across the mesh is 4 volts. The battery's rated energy capacity is 15 kilojoules. Users report that the vest only stays warm for 22 minutes despite expectations of at least 30 minutes of heating. An internal report concludes that the issue itself lies in inefficiency energy use or thermal losses elsewhere in the circuit, not with the heating element itself. So determine whether the duration of the heating reported by users is consistent with the energy transfer to the heating mesh based on the data provided. Show your reasoning. The team wants to reduce power consumption without changing the battery. Suggestions justify one electrical change to the circuit design that could extend the heating time and discuss a potential trade-off in performance. Then finally, evaluate the claim made in the internal report that the underperformance is not due to the heating mesh but to inefficiencies elsewhere in the system. In your answer, consider both electrical and thermal processes. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, let's work out the power delivered to the mesh. P equals VI, 4 times by 1.5, it is 6 watts. Now the energy used over 22 minutes is therefore E equals P times by T. So it's 6 times by 1320, which is the number of seconds in 22 minutes. So it's 7.92 kilojoules. Now the expected maximum usage with full energy, we know is going to be time, is going to be equal to 15,000, the energy capacity, over 6. Okay, which is going to be the power, so that's going to be 2,500 seconds, which is 41.7 minutes when you work it through. So what that tells us is that the heating vest only heats for 22 minutes, much less than the theoretical value. So therefore, the significant energy is not being delivered to the mesh, which is needed for it to work, so support that there must be a loss elsewhere. Now, how could you then reduce the power consumption without changing the battery? So you've got to think of a suggestion of reducing the current. So you could think about increasing the resistance of the mesh to reduce the current whilst keeping the voltage of the battery the same. So this will reduce the power, because you know P equals I squared R. So therefore P will drop if I drops. So the energy will therefore last longer. So therefore there'll be a lower power over time. So the trade-off is that there'll be a lower heat output, so the user will feel less warmth, reducing the perceived effectiveness, but it will occur for that at least 30-minute time period. Now in the final question, the heating mesh appears to work as expected based on its calculated power consumption. Now if the heating time is shorter than the battery capacity allows, energy must be being lost or diverted elsewhere. So the likely sources could include internal resistance in the battery, energy loss as heat in connecting wires, in the control electronics, or poor thermal insulation. Now some energy may also be lost in regulation or control circuits or lost via heat escaping from the vest. So overall, you can conclude that the claim itself is plausible. The data supports that the energy losses occurring upstream or downstream of the mesh, but not in the mesh itself. Our next question says, state what is meant by the EMF of a battery, and figure 10 shows the circuit diagram for a battery powered torch. The circuit contains 3 identical light emitting diodes and a resistor R. The current in the circuit is 44 milliamps. Calculate the number of electrons that pass a point in the circuit in 37 minutes. So pause the video now, then unpause the video when you want to go through your answer. Right, we got to learn the definitions of key terms. So EMF is the amount of chemical energy transferred or amount of energy converted to electrical energy for 1 coulomb of charge. It's per coulomb of charge. Now our next question, we know that charge is equal to current times by time. Time has to be in seconds though, so 37 minutes turns into 2,220 seconds by doing 37 times by 60. Remember, 44 milliamps turns into amps, so you get 97.68 coulombs. So the number of electrons is 97.68 divided by the charge of one electron, 1.6 times 10 to the minus 19 coulombs, 6.1 times 10 to the 20 electrons. Our next question says, a student was given a block of conducting putty of mass 43 grams. Show that the volume of the conducting block was about 8 times 10 to the minus 6 meters cubed. The density of the conducting putty is 5,300 kilograms per meter cubed. The student formed the putty into a cylinder. Coins are pushed onto the ends of the cylinder as shown. The coins each had a crocodile clip attached and an ohmmeter connected across the putty. Determine the resistance of the cylinder of the putty. So the diameter of the cylinder is 12 millimeters. The resistivity of the conducting putty is 4 times 10 to the minus 3 ohm meters. And then the student then made a cylinder that had a large resistance. How could the student use the putty to make a larger resistance? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that volume is mass over density. So we turn our grams into kilograms, so 0.043 kilograms over the density of 5,300. So it's 8.1 times 10 to the minus 6 meters cubed. In our next question, we can work out our area, because area is pi r squared because it's a cylinder, so the cross-sectional area will therefore be a circle. So you can work it through, remembering to turn any diameter into a radius and the millimeters into meters. So you can get 1.13 times 10 to the minus 4 meters squared. Now we've got an area, we've been told a volume, so therefore we can work out a length, which is needed for the resistance equation. So what we can therefore do is say that the length is equal to the volume over the area. So the length is 0.0716 meters. Pop that into the equation. That resistance is equal to resistivity times by length over area to get 2.54 ohms. Now finally, how could you make a larger resistance? Well, you make the cylinder of a longer length, or the cylinder of a smaller radius or area, because from the equation R equals rho L over A, a longer length or a smaller area will change the resistance to increase it. So that brings an end to our revision session today. If we've been successful and learnt in today's revision session, we should be able to answer A-level physics exam style questions, assess our understanding on A-level physics, and understand what topics we need to improve upon for A-level physics. So thank you so much for watching this revision session on AQA A-Level Physics, Paper 1, Electricity, focused on the topics of current, resistance and resistivity. Thank you so much and have a lovely day.